Okay, so here we are going to use another example, more realistic data, real data, and apply the linear regression model. So our topic is the relationship between education and wage. So this is one of the most popular example in linear regression model. Of course, actual estimation requires more details and additional issues addressed, but I will simplify everything and we'll consider the relationship only between hourly wage Y and years of education X. Okay, so beta 1 is called the returns to education. So when you stay in school for another year, how much your hourly wage will increase, right? And beta 0 is the expected wage if your education is 0, right? So this is an example where beta 1 is meaningless because in reality, like there is no one, it's really hard to find anyone who has 0 education. So beta 0 does not realize at all in real world. So what we are interested in is only in beta 1. So let's estimate. Go to the data. Our data looks like this. So we have education, years of education, and hourly wage. So how many data are there? More than 2,000. 2,245 44 observations are available to us. And let's look at that. So 12 years of education is high school graduates. So 17 years, 16 years is 4-year college graduation. And maybe 14 years of education is 2-year college graduation. 15 years is maybe dropout. 17 years, maybe 1-year master program. 18 years, 2 years master program. Something like that. So 10 years is possible if you drop out of high school. So you have also wage, hourly wage, like $11 per hour, $5, $6, $4, you know. So let me show you the scatter plot first. Scatter plot looks like this. So it is not clear what's going on because X variable, the education variable, is collected at only at integers. So of course, like 12.1 year is not possible in our observation. So a lot of observations are lined up exactly on 12 or 16. So then let's make a trend line. Trend line is here. So another problem is there are too many observations. So there are a lot of dots around here and there. But it is not easy to tell how many observations are there. Alright. So anyhow, that is a big problem. And I think it should be an error. There is an outlier who is at 0 education. I'm not certain it's maybe typo of 10 or I don't know. Nothing can be done now for me. But any outlier is okay in this case because it is only one observation relative to more than 2,000. So it shouldn't be a big problem. Anyhow, the conclusion is scatter plot may not be helpful because there are too many observations and the data are integers. So we are going to move to regression analysis. Choose regression here. And Y variable is wage and X variable is education. And the first one is label. And now let me show you 90% confidence interval. Let me try 90%. And I clicked here. Click, oh. So I don't know what happened. So let me choose the data range more correctly. Then, oops. Oops. Better. So X is education and Y is wage. So let's click. Oh yeah. So I made a mistake in choosing the data range. Okay. So pretty much the same table. We have different numbers. And first, you can see we also have 90% confidence interval and 95% confidence interval too. And the observations are, number of observations is 20 to 44. And point estimates and standard error. And what is interesting here is intercept is negative number, right? That is also, you could see that from this trend line. If you extend trend line, it goes below 0 at the intercept, so it is negative. But so this means interpretation should be if your education is 0, your expected wage is minus. Of course, that does not make any sense. Wage cannot be minus, but not a big problem because zero education is rarely observed, almost non-existent, right? This observation must be an error. Then it is not a big problem. Estimation at this point does not make much sense. Okay, let's go back to the slide. This is how it works. And now let's check together for your practice and for the validation of like if Excel is doing well. So we are going to use the point estimator and its standard error, right? So these two numbers, we are going to use these two numbers and we will calculate these numbers. That is what we are going to do as a practice. So simply the point estimator is 0.743 and the standard error is 0.046. Okay, so that means interpretation is on average, if you stay in school for another year, if you or do 1 year master program, the hourly wage will increase by $0.743. That is what it tells. And then, what is the confidence interval? Can you calculate that using this one? You may use Excel directly. That is also possible. Just open, as I uploaded the data file with this lecture. So download the file and try to make this table by yourself. And you may calculate the number from here. Okay, so 95% confidence interval, Z value is 1.96. You can also do that on Excel. So let me do it. So first, I will calculate Z alpha over 2. So remember, that is top 2.5% value. So in terms of cumulative probability, it corresponds to 97.5%. So if you use norm.s.inv, standard normal inverse, at 97.5%, then it is 1.96, approximately 1.96. I'm going to use that. So then first multiply this number to the standard error. That is margin of error. And the margin of error is added and subtracted from the point estimator. Then these two are the confidence interval for 95%. So compare. Like, it's hard to see what is going on. So let's simplify. So you have numbers like this: A326, A326, 6537, 6538. So there is a small difference. That is because I'm using normal distribution approximation, but Excel uses T distribution, which is different but similar to normal distribution. Anyhow, the difference is really small, and Excel is doing well. What Excel calculates is basically what we learned. Okay, what you do is well, good. And next, let's do the hypothesis test by ourselves. So again, we have point estimator and standard error. From here, calculate the t-statistic and see if it is rejected at 5%. Two-sided test. Your belief is beta 1 equals to 0. So pause the video, and it is better to calculate directly on Excel. Okay, let me do this on Excel. So remember, the t-statistic is based on the estimator minus your belief. Minus belief is 0, so belief is 0, and divide that by standard error. That is it. This is the t-statistic. T-statistic is 16.29 something. Exactly the same thing, right? These two numbers are exactly the same thing. So that's how the t-statistic is calculated, right? So t-statistic is correct. 16 point something. So the answer is C. By the way, the number is different here because I use those approximate numbers, right? Those approximate numbers rounded at the third decimal place, right? But if you do not round, so the rounding error is quite huge, right? So the difference is coming from the rounding error. Please understand. So and this t-statistic is compared with plus minus 1.96 because the significance level is 5%, right? So, and it is obvious that 16 is much greater than plus minus 1.96. So it is far outside the acceptance region. So you are going to reject the null hypothesis. The standardized difference is too much. The difference is really huge, so your hypothesis must be rejected, which is good for you because if it was 0, it was not rejected, that means your regression model is pointless. X does not explain Y. Okay, so also then, based on the t-statistic, you can calculate the p-value. Let me do that. So this is the p-value, and to calculate the t-statistic, I will calculate its cumulative probability. And that take 1 minus that, so it is 0. So multiply 2 times that is, so think it this way. So this probability is probability on the right tail, right? On the right side tail, probability, sorry about that. So this is cumulative probability. So cumulative probability is probability smaller than 16.29 something. That is 1%, 100%. And then the right side tail probability is 1 minus the cumulative probability, that is 0, right? So in the standard normal distribution scale, 16 is a huge number. Approximately plus minus 4 is already 99%, 99.999%. So 16 is huge, so p-value is 0. The p-value is 0, 0.000%. So this is how you calculate the p-value, but the number is too large, so anyhow it will be 0. Okay, so as I said, there are some differences between what we calculate on Excel and what I show you on slide and what Excel calculates because of the rounding error. One thing is the rounding error, and another thing is I use standard normal distribution approximation, but Excel uses an old school t-distribution approach. So t distribution is not wrong, similar to the normal approximation, but normal approximation is more unified approximation. So I recommend you understand the normal approximation first. Okay, so this is a replication of what Excel does. Now I am going to do my own hypothesis testing based on the Excel results. So suppose that I believe that the returns to education is $0.7, right? If you attend 1 year master program, your hourly wage will increase by 0.7. That's my belief before looking at the data. But according to the data, it's slightly greater than my belief, right? Slightly greater. Then can you reject my null hypothesis or not? By the way, it is one-tailed test. So my belief was actually 0.7. The returns to education was $0.7 or lower, at most $0.7. So if it's greater than 0.7, then you have to give up your belief. Now I will give some time, use Excel this result to calculate the p-value. So it may need time. You will need time. So pause the video here and calculate the p-value. Okay, if you have not finished, please stop the video. Pause the video now. So now we are going to start from t-statistic. T-statistic based on different hypothesis is like, say, the point estimator minus your belief. Your belief is 0.7, so I subtract 0.7 and divide by standard error. That is the new t-statistic. It is 0.946, so pretty much close to 0 relative to 16. 16 was a huge number, but now it is close to 0. So p-value. I am going to calculate the p-value, but the p-value is calculated based on one-tail test. It is upper tail test. So we are concerned only on the right-hand side, right? So only on the p-value is calculated if the standard normal, the p-value is the probability greater than the t-statistic. So that is 1 minus. So we are calculating probability greater than the t-statistic. So we have to calculate the cumulative probability and take that from 1. Subtract that from 1. This is the p-value. So p-value is, say in percentage, p-value is 17% in this one-tail test. So the p-value is C, right? So t-statistic, rounding error, there can be rounding errors, and upper tail test, p-value is 17%. So 17% is high enough, and usually we do not reject any p-value above 10%. So your null hypothesis is not rejected. You may think it this way. So 0.7 and 0.7, so your belief is 0.7, and the estimate is 0.743. The difference is 0.043. That is smaller than the standard error. That's why the t-stat is 0.9. So the difference is slightly smaller than the standard error. And that is, and remember, this is usually compared to like 1.96, something like that. So it is relatively small. So the difference is small. So your belief is not rejected. Okay, so this was practice using real data, right? As I showed you, you may utilize the Excel results, and also using them, you may do your own hypothesis testing. That is possible. It's pretty simple, right? Okay, so in the next video, I am going to start the prediction part. So earlier I introduced you 3 parts. The second part is the prediction. So we will start the second part and the third part in the next video. Thank you for watching. See you later.